Okay, we should be live. And I think it's you. Oh, there you go. Okay, so we should be live. Welcome for another live stream on the assumption of physics. Today, we have a guest that is going to talk to us about his work on PhysLean, which is basically a project that is trying to put all the math that we have in physics and all the physics into Lean, which he is going to tell us exactly what it is. So if I'm just trying to make sure that I don't screw the live like I did the last time. So it seems to be public and everything seems to be working. So I'll please, Joseph, introduce yourself and tell us a little bit about what you do.
My name's Joseph. I used to be a postdoc in physics, but now I work in computer science. And yeah, basically a year and a half ago, 2 years ago, I asked myself the question of what do I think the discipline of physics is going to look like in 100 years' time? And I think one of the things that stands out to me is that the role of computers in physics and the way that we do physics is going to be fundamentally different from how we're doing it now. Whether that be the use of AI or whether that be the use of things called proof assistance, which we're talking about today. So I thought I would kind of give you a quick demonstration of proof assistance, first of all, and then what the project PhysLean is all about. So I'm going to share my screen if that's okay.
Go ahead.
Yeah, so let's start with a Pages document. So imagine we're writing a physics paper called like Physics of Nonsense on something like Pages or on Microsoft Word or something like LaTeX, which is what physicists would tend to use when they're doing this sort of thing. We could write things like what could we write? We could say, this paper is based on the fact that 1 is equal to 1 minus 1. And Pages does not complain. The fact that 1 is not equal to 1 minus 1, it doesn't care. It doesn't care that you've written something which just doesn't make sense. It lets you do it. Or it doesn't care that you've written something that's incorrect. We could also write things that are just don't make sense. So we could write, for example, let f be a function from the natural numbers. So that's like 0, 1, 2, 3 to the natural numbers. And let a be an integer. And then we could write, let's assume that f is equal to a. So you can't assume that a function is equal to an integer. It does not make sense. So this sentence or this paragraph here in mathematics, it doesn't make sense. But Pages and Microsoft Word and LaTeX, they won't complain about that sort of thing. They'll let you just do it. And this leads to problems in, for example, the physics literature, where we're writing documents in these sorts of things. And there are mistakes like this that happen all of the time. So kind of the idea behind a proof assistant, something like Lean, which is the proof system that I work in, is that you can't make these sorts of mistakes. It doesn't let you write things that are wrong, or you can't prove things that are wrong. And this allows you to have like much more confidence about what you're doing. And you can also, because the computer kind of understands what's going on, it kind of understands what a function is, it understands what a natural number or an integer is, it can help you when you're trying to prove things. So that's the other side of this. Like these proof assistants, these interactive theorem provers can help you prove things. So I thought I would rewrite this in Lean, one of these proof assistants. So I'm on a website here, which is basically an online version of Lean called live.lean-lang.org. And we can write things very similar to how we would write the definitions and the things that I just said in physics. I'm just going to write import mathlib. We can ignore that for now. But let's say we wanted to base our results on the fact that 1 is equal to -1. So 1 is equal to 1 minus 1 is equal to 1 minus 1. So we could go something like lemma, and we could go fact. We could go, let's say that 1 is equal to 1 minus 1. And in something like lean, you have to prove these things. I'm just going to refresh my screen a second so that the server starts. So it doesn't complain yet, but what we'll find is that lean won't be able to prove this. So we'll never be able to tell lean that this is true. And that means we won't be able to use this really in things that follow. In fact, if we try some of lean's tactics, which you can use to do proofs, they won't work. So omega is a sort of tactic that you can use with numbers to see if it's true or not. And it won't work in a sense. But if I try to say that this fact is not true, then I can prove it. So you can't make incorrect lemmas or incorrect results in lean. Similarly, so if I go on to this next paragraph, I can go, let's say I have lemma, fact 2, and let's say I have a function f that goes from the natural numbers to the natural numbers, and I have a that's an integer, and I say let's assume that f equals a, and let's try and just prove true. We can see that lean here complains. It puts an error under a. And what it's basically saying is that the type of a, the sort of thing that a is, it's an integer, cannot be equated to a function. You just can't write that. And in the same way that Pages or Microsoft Word or LaTeX will give you a squiggly underline when you've made a typo in a word, lean gives you these sorts of errors when you make mathematical mistakes. And in that sense, it's very powerful. So yeah, the mathematicians have been kind of using this fact for a while to write down basically a large chunk of mathematics into one of these theorem provers. And this means that we know that the mathematics in these libraries is true, and that we can use it to do other stuff. And this project is this mathlib project that I talked about. So hopefully that kind of, makes sense a bit.
So if I can interrupt, so what is sorry, what is omega, and how do you see that something works and doesn't work? Because
Yeah,
it's
right.
not clear to me.
Good. Okay. So omega, so sorry is like, sorry, I'm gonna prove this later. Don't worry about it. I'm gonna come back to it. So if I remove the sorry, it will give me an error saying, so basically everything after the by is I'm trying to prove this statement. So sorry is like, I'm gonna come back to it later.
Okay.
It adds, yeah, you don't want sorries in your proofs, but it's kind of like a placeholder. So omega is one of these powerful tactics that I was kind of talking about. So omega is a way for lean to prove things about numbers. So it can prove results about natural numbers, about integers, and it does it automatically. So this is kind of the other side of these theorem provers, is that they help you prove things in an automated way. And this can be very powerful because you don't have to do a lot of the work yourself.
Do you know what they use underneath? What type of technology do they use?
So it might tell you here, so one of the benefits of these things is that because Lean knows what everything is, you can hover over it with your mouse.
Mhm.
It will tell you, for example, 1 is a natural number, A is an integer. So if we go over omega, it will tell us what this tactic does.
Okay.
Yeah, I'm not an expert on the inner workings of these.
I did some of these things a long time ago, expert systems that use the inference engines to do. So I was wondering whether this is an inference engine or it's something different. And if it is an inference engine, what type of inference engine it is, that's yeah, I like in another life 20 years ago, even I wrote my own small thing. So I was curious. Maybe I'll have to just to go and look at.
Yeah, no, yeah, I couldn't tell you,
Okay.
unfortunately. These are one of these things where I'm kind of using it as a black box and
Yeah,
it
yeah,
just
yeah. That's
works
fine.
for me.
At some point, everything becomes a black
Yeah,
box in
so at some
engineering.
level
You
you have
can't.
to.
Yeah. Okay. Okay. Go ahead. Go ahead.
Yeah, so what's the point? I mean, what's the conclusion of all of this, right? The conclusion is that these theorem provers, you can write things that look like lemmas, which you have in maths, and you can write things that look like definitions, which you also have in maths. So you can write mathematics into it. It will check it for correctness, and it will help you prove your results. So there's this library called Mathlib. Let me go on to the GitHub for this project. This is a library of results from mathematics written into one of these theorem provers. So if we go into the main file, we can see that it's got a bunch of different subdirectories related to a bunch of different areas of mathematics. So algebra, topology, category theory, group theory. It covers a wide range of mathematics. And in each one of these folders, there's subdirectories and there are these lean files. And if we open a lean file at random, the lean files have theorems and definitions and lemmas, where this one only has theorems, which you can use to prove other things. So it's basically a collection of a large collection, a very large collection of mathematical definitions, mathematical theorems that we know are correct and that you can use because Lean can use theorems that you proved in the past to prove other things. And yeah, we're sure of its correctness. So what I have been working on, like I said, is really where do we think physics is going to be in 100 years' time? And in my opinion, physics is going to be something like this. Maybe more evolved rather, but something of this sort of style. So I'm working on a project and I made a project called Fislean. So Fislean is basically the physics version, or is attempting to be rather the physics version of Mathlib. So it's a project to digitalize results from physics into Lean 4. And so let me go into the GitHub. There are a number of benefits of doing this. One of which is you can search it, you can easily find results in it. You can use it, everything only has to be done once. So yeah, this is what the repository looks like. And it's got a bunch of different areas. So it covers, well, it's got folders for like classical mechanics, condensed matter physics, optics, particle physics. A lot of these folders are currently empty. They just have a placeholder folder in. But some of them, specifically the ones related to more like quantum field theory, happen to be my background. Particle physics have results in them. So the field for quantum field theory, for example, has results about perturbation theory. So perturbation theory is one of the ways that we do this thing called quantum field theory. And there's a bunch of results and a bunch of things about about perturbation theory. In particular, it's got something called Wick's theorem. Wick's theorem is kind of one of the foundational principles of quantum theory, and it gives you these things that people call Feynman diagrams. You may have seen these like diagrams where particles come in and particles go out. And Wick's theorem is like the precursor to Feynman diagrams. But yeah, so this is a library, and the idea is to expand this to go into different areas, to build an interconnection between the different areas of physics, and slowly build it up so that people can use it, people can contribute to it. Yeah, I mean, so that's basically the idea of Fislean. There are a number of other things. So one of the things that I've been mentioning is that it allows you to search. So there is, as of yesterday, actually, a form of Lugo, which is kind of like Google, but for lean, for Fisting. So if you wanted to find results about, for example, the Higgs boson, you could search Lugo and it would tell you all of the results in Fislean about the Higgs boson. In theory, you should be able to click on these and it should take you to the results in the library. It currently doesn't, but it will get there at some point, probably next week. But yeah, you can search for random stuff. So we can search for the harmonic oscillator or harmonic, and it will give us a bunch of results about the harmonic oscillator, which are in Fislean. So yeah, so that's kind of the gist. That's kind of like what this project's all about and where I think it's going to go. And yeah, the main components of it.
Okay, so if people have questions, they can put them in the chat and then I'll relay them. I'll be interesting to see like a small a real example and with the nitty-gritty detail so that we can see how it looks.
Yeah. Well, okay, why don't I open, let me open the project in something that can actually
Yeah.
read Lean. So when you open Lean, I'm opening it in a program called Visual Studios, which is made by Microsoft, and it's basically one of the go-to like text editors. Or like
It already recognizes the syntax, it seems. It has the syntax
yes,
highlight.
yeah. So there's a bunch of like background stuff that goes on that makes Lean usable for Visual Studios. Like I said, someone's made a syntax highlighter. You can hover over things and it will tell you, for example, let's say we wanted to, let's pick a definition. So this is a mathematical theorem. It's about eigenfunctions of the harmonic oscillator. And one of the great things about Lean is that you can hover over things and it will tell you what they're defined as. So eigenfunction, it tells us this is the nth eigenfunction of the harmonic oscillator. We can highlight over, for example, real pi, and it should hopefully tell us that that corresponds to the number pi. So the program itself, so unlike, for example, Pages, the program itself knows everything about the equation, right? You could follow all of this back to like the foundational definitions of type theory if you wanted to. But yeah, so the equation knows what is going on here, or Lean knows what's going on here. Yeah, so the basic idea is that when you're writing the definition, it has to make sense in terms of like things have to be properly defined. You can't equate a function to an integer because that's not defined anywhere. It doesn't make sense. And when it comes to proofs, I usually do these things called tactic proofs. There are other ways to deal with proofs.
So
So
let me understand at a higher level. So this is a lean file, and the
yes.
hill file is basically a collection of lemma, definition, stuff like that.
Yep. It's a collection of lemmas and definitions. It's ordered. So this lemma can use results from everything that comes above it
Yep,
in the file. You can
but not
input
below. So it's like
it.
C,
You
not
can't
like
use
Java.
below. No, yeah, you can't use below. It's
Okay.
ordered in the sense that if I make a change down here, you'll see. So if I make a change here, you'll see this yellow bar on the right-hand side of the screen.
Oh, it's recompiling everything below.
Yeah, it re goes down the lean file and makes sure that you haven't made a change that's going to break something for front. So if I change a definition, for
Right.
example, it will recompile everything and check whether that definition has broken anything.
Okay, so yeah, okay, it's different than a normal programming language because there is no executable, right? It's when you write, it will go through it, check that it's correct, and that's it. There's nothing else to do.
It won't check files that depend on this file automatically. You have to get it to do that at the end.
Okay.
It only checks one file at a time. If it was checking everything in one go, if you made a change like to the definition of an integer, it would take a very long time.
Right. So when I say that there is no build system, like typically when you have a C, Python or whatever, there is
Yeah,
you just write the code and you click a button and it builds and it does the tests. And here,
yeah, there is. So
oh,
if
there
you
is.
see my terminal, this lake build,
Okay.
that builds the whole project. So that checks, what that does is it checks every single definition and every single lemma.
Okay.
Whilst this interactive bit just checks your file.
Okay.
Um, yeah. So I could break something here, break something in a further file, in a file like that it depends on this. And I wouldn't know that until I built it.
Okay. Okay,
So
I have a couple of questions from the chat. So
okay.
one is, do you worry that starting formalizing from the top of physical theory, like quantitative theory, instead of classical mechanics and moving up, quantization, etc., would introduce unnecessary complexity and a lot of refactoring later?
Um, maybe. I think so. One of the things that MathLib has is this policy to refactor when necessary.
Okay.
And I think that is like a great thing to have, right? You start with something, and then if you need to change something, it might be a lot of work, but you should do it because if this is going to be the library for the future, a lot of work in the past, a lot of work now is going to benefit the future. In terms of like where do we start? So one of the reasons I did quantum field theory rather than like classical mechanics to start off with is that one is my background as a physicist. I used to do quantum field theory. I used to be in high energy physics, and I wanted to do research level results. I wanted to do results that I could go to researchers in my area and be like, look, you can take your research and you can write it into one of these theorem proofers rather than going like, oh, look, you can do classical mechanics. Which actually doing classical mechanics, there are probably technicalities there which make it quite difficult.
Yeah.
But if you wanna go to like, I wanted to go to people and go, look, doing quantum field theory, you can do your research in this. So that was kind of like a, like a promotional thing, I guess.
Yeah,
Uh,
like I completely sympathize with that. Whenever you have a project, you have to give something where people find it immediately useful. Otherwise, I'm just not gonna pay attention to you. So
yeah.
I totally understand. Again, in the previous slides, when I was building tools for a physicist and other researcher, that's what you do. Like they only want to have they want to see an example so that they can go and sort of do something similar and get something useful right away. So yeah, I totally understand.
And more generally, like I think with a project like this, the key part of it is that you should have fun doing it. And because of my background, like I find doing quantum field theory fun. So that's what I started with. And maybe it was better to do classical mechanics first and to lead to like quantum mechanics and quantum field theory. But that's not like I wouldn't have found that as fun. And you know, we have to have fun when we're doing this other stuff. So it's kind of like a selfish motivation, but it's a motivation nonetheless. Um,
Yeah, you have to keep your own
Sanity and
interest, yeah, and sanity of mind.
yeah.
So another thing from Cram is, could you basically start like after? First, I want to see a little bit more of detail of something already done, but it would be maybe useful if you could create something from scratch, and so that we can see sort
Yeah,
of how
yeah,
it
yeah.
works. But okay, so let me just understand. So the namespaces are just namespaces like if you can scroll up, I just want to go and see. Okay, so the import it's like Java, you're importing symbols whatever.
Yeah.
Namespaces,
Yeah, you're importing the definitions and the theorems that have come before it.
yeah. And the namespaces, I assume they are like in C so that you can do whatever you want. The namespaces don't have to match file names and stuff like that. Like you can basically do whatever
Yeah,
you.
yeah, yeah. They're just like, so if I hover over a name, like eigenfunction, the actual name for that is the namespaces
Yep. Yeah, yeah, yeah.
with eigenfunction at the
Yeah,
end.
yeah. So
And
it's
then you can
something.
define
Yeah.
variables and stuff.
Yeah. So my question was just whether it's like in Java that you're enforcing that the namespace is actually a directory structure, or it's like in C where you can put the namespace wherever you want, and then you hope that you have a good directory structure so you can find the files. Okay, so then a variable then is just the definition of a variable, and I assume the Q is the name and harmonic oscillator. No, Q is the type, and harmonic oscillator is the which one is
No,
the
the other
type,
way
which
around.
one is the name?
Harmonic oscillator is the type, Q is the name. So
Q
if
is
I
the
give you
name.
the definition of harmonic oscillator,
Ah, there you go.
harmonic
Structure.
oscillator is defined as a type. The structure is just a special type of type.
Yeah.
Uh, yeah, type is just, like similar to a set, but not quite the set. Um,
Okay.
and
So the type is afterward, and it's using a lot of like Unicode for all the symbols.
yeah, so I mean, it's like if I wanted, it's like LaTeX. You type it like LaTeX. So Visual Studios, if I wanted to type
Oh, but
like
so it's just a rendering of Visual Studio that renders it like this in the
yeah,
file.
I believe
Ah.
so.
Okay, so if I look at the text file with a text editor, I would actually see \r. That's what I would see.
This I don't know actually. I don't
Ah.
know. I think it's UTF-8. It's the
Okay, so it is Unicode.
it's Unicode, yeah.
Okay, so it's
My
the
knowledge of this
editor
stuff
that is
is
converting the string into a Unicode. What they're called? The points. I forget what they're called. Okay, so the file is actual Unicode. If I open in
yeah,
a
yeah, yeah.
file, I better have something that is Unicode. Otherwise, cool. This is something that again, 20 years ago, I was futzing around with writing my own computer language to do some things, and I was using Unicode instead of the same way. But of
Yeah,
course, it was
but
just more.
this reminds me that one of the things that physicists love is notation, right? We love like bracket notation for in quantum mechanics. We love index notation. And lean is really powerful. Well, lean is like really good in the sense that you can use notation. Um, so let me give you an example of this. So one of the things that I have done recently is implement index notation into lean. So where shall I look? Relativity tensors or Lorentz, complex tensors. Let's see if we have an examples. So you can do so in in Fistline, you can use index notation. So at Fistus, we would usually write these like up and down, but you can imagine these alpha and this alpha prime being like up indices on this epsilon. And
Okay.
you can do things like permute the indices on both sides of the equation. And lean will these things are tensors, and lean will take account of that permutation. Um,
Okay.
so what happens here is that lean this gets sent to what's called an elaborator, and lean turns this syntax into something it can understand. Um, it turns it into an expression based on basic definitions. So you can use this you can define like clever notation, which makes the code look pretty, which lean then goes through and checks changes it back to its original thing or
Okay,
changes
so
it.
you can basically do some type of syntactic sugar that then gets reconverted in your abstract syntax tree that then Lean can use it as if it were anything else. Okay, that's
It's
interesting.
yeah.
Which means the parser must be doing funny tricks of taking that thing and give it to something because at that point the definition of that notation is just another Lean file, right?
Yes, exactly. It's just another lean file that takes
Cool.
that definition of that notation, does some like tricks with it to account for the fact that the alpha prime is on the left here, the alpha is on the right, the
Yeah.
alpha on the left is the other way around here. So it adds like the correct mathematical object to permute those two indices.
Yeah, yeah, yeah.
You can
So
obviously like contract indices in the same way that you would in
And you can use anything as some kind of infix notation like that, or there are only specific type of symbols that you can reuse?
Will use it. I could put cat here if I wanted to.
No, no, I mean, I think the operator is the vertical bar, right? The one that separates.
Yes, this is ideally I would like to get rid of this vertical bar.
Right,
Um, but yes, that vertical bar is part of the syntax. It says,
right,
okay, the thing on the left is the tensor, the thing on the right are the indices of the tensor.
right.
Um,
The vertical is what tells the parser that you have two different tokens on the two different sides. So,
yeah, basically, it helps it recognize this structure.
okay, interesting. Okay, so let me go back to the chat. There were a follow-up question. I wonder what dependencies from MATLib are the most useful, number, manifolds, vector spaces. Have you found something missing or and implemented it yourself while doing your QFT work?
Yeah, differential geometry is just not there. Basically, it is there. Like you can do differential equations, you can do certain things about tangent spaces. Um, there's a part of differential geometry called principal bundles,
Hmm,
which is basically the most important part of differential geometry for something called gauge field theory.
okay.
Uh, Gauge field theory is the thing that gives us force in the world. So it's the thing that determines the electromagnetic force. It's the thing that determines like the strong force and the weak force. And to do that properly, you need principal bundles. You can do it improperly without principal bundles, but then that if you did that in lean, this would go kind of back to the refactoring question. You'd have to kind of like refactor that in the later to include principal bundles. Um,
So
which
lots of stories, right? If we understand correctly, lots of stories.
Well, yeah, you could. I mean, you could probably do it without sorries
Okay.
for a bit, but then like your definition would not be the correct mathematical definition. So you'd somehow have to connect that definition
Yeah.
to the correct one. And th this happens a bit in this project, right? The definition of a harmonic oscillator
Hmm.
and the quantum mechanics behind the harmonic oscillator isn't the right. There's no. I haven't put the foundational principles in that yet. I mean, that is. I choose to start. I chose a starting point, which was to assume that you have the Schrodinger equation for the harmonic oscillator. I don't prove that the Schrodinger equation is the thing that gives you quantum mechanics, but that can come later, and that will involve some refactoring. Hopefully, not a lot of refactoring. Like ideally, like somebody that knows just the harmonic oscillator should be able to come into this and not have to worry about foundationals or quantum mechanics.
Mhm.
Um, but yeah, so this thing does happen. I mean, so you could imagine like doing electromagnetism, for example. You could imagine defining the electric field and the magnetic field, defining Maxwell's equations, proving a bunch of things about those. Eventually, you'd want to connect that back to gauge field theory, which is the correct mathematical formulation of this. Um, but I think something is better than nothing. So like if somebody wants to do electromagnetism, you should do electromagnetism. We'll deal with the consequences of connecting that to gauge field theory later, if that makes sense.
So let's go back to the harmonic oscillator example and go through it a little bit more.
Yeah, should we go through that in a bit more detail? So yeah, why don't we start? Okay,
So let's go to the beginning of the file.
beginning of the file.
Okay. So we said, I know because it was the other file that where we clicked
We were
on.
looking at.
So
So
this is. Go ahead.
yeah.
Go ahead.
Well, yeah, sorry. So this isn't really the beginning of the harmonic oscillator story because to define the harmonic oscillator, you first have to define the Hilbert space. Uh,
Okay.
so really, there's another file which before this called the Hilbert space file, and so this is one of the nice things about having like a monolithic library for a project is that you can reuse things all over the place. So if somebody else wants to do a one-dimensional quantum mechanical system, they can use the same definition of a Hilbert space. You don't have to redefine the Hilbert space for the harmonic oscillator and redefine it for, I don't know, the reflectionless potential or something like that. You can reuse stuff all over the place. Um,
So the namespace is recursive. So the one dimension namespace now is a sub namespace of quantum mechanics.
Yeah.
Okay, okay, interesting.
Yeah, so this is so really I think I could do quantum mechanics dot.
Right, right. That's how I like. Yeah, typically, if I see another namespace declaration to me, I'm changing the namespace. Instead, I'm
Oh
going down
yeah,
in the namespace.
sorry. This is
Interesting.
preferred. Yeah, yeah, yeah. No, this is going like this is keeping on going. Um,
Okay, no, non-computable. What is that? Non-computable section.
good, good, good. Yeah, so non-computable, what does that mean? Non-computable. Well, actually, there's a bit of a typo there. I don't need that. What does non-computable mean? So Lean is an executable programming language. So I can define a function that takes the natural numbers to the natural numbers. And let's say it doubles the natural number.
Okay.
Okay. So I can normally evaluate that function. So I can do eval and then I can do find f on one, and over here on the right hand side of the screen, I get the answer.
Oh,
So
okay.
it's so Lean is an executable programming language. So it allows one of the benefits about this is it allows this interface between uh, theory and simulation, for example. So you can write down mathematical theories, mathematical definitions, and you can use those definitions to do executable programming languages, um, which is kind of like the programming side of these theorem provers. You can also use these to check programming language programs for bugs, for example.
Yeah, do you have like a unit test type system where you can put a bunch of evals and check that they are what they should be?
Uh, I guess you could, yeah. I don't know if people do this.
Right. But again, you know, my background engineer, like to me, like the writing the unit test, like oftentimes you write the unit test beforehand so that you can see how the syntax looks like before actually implementing, and you find. So anyway, so
Yeah, I guess the fact that like, you're pretty confident that you've made a definition right from the fact that if you're trying to prove theorems about it,
that
uh,
is true. Yeah,
that is true.
yeah,
You're either going to be able to prove the theorems or you're not going to be able to prove the theorems.
that is true.
But you can't, I mean, Lean will let you be stupid. Don't get me wrong. You can write a stupid definition in Lean and you can prove a bunch of things about that definition.
Right.
But it won't let you be wrong.
Hmm.
Uh, so what non-computable means
Yeah.
is that these functions they're not executable, essentially. So they don't have that feature that I can do like f equals one and it gives me an answer.
So
So
you,
this
you
is
can't evaluate them, basically. That's what it's meant.
unevaluated.
Okay.
Yeah. This is annoying. I mean you can't get around it. Like some things are just like inherently non-computable.
Mhm.
Uh, Ideally, in this lean, we kind of want as much as possible to be computable so that if somebody did want to use it to write a simulation, to do a simulation with, they could use the same definitions. Uh,
So things
and
like theorems and lemmas are non-computable, I assume.
theorems and lemmas are non-computable.
Okay.
Yeah.
Yeah.
Um, they don't care. Like for Fermat and lemma, they don't care about the kind of like the output of that, the thing that the proof. They don't care about the proof of the theorem and the lemma. They kind of ignore that. Um, What's the definition keeps account of the definition.
Okay, well, there is more activity on the chat. Let me, let me go through
Yeah.
that. Means it's unconstructing. Comment non-computable effectively means it's not constructive using stuff like lem or the axiom of choice, right?
Yeah,
Okay.
exactly.
And what about real function? Does it have floating point numbers?
Ah, good. It does have floating point numbers. Um, these are different from real numbers in Lean.
Okay.
So you have a type called float. Let me see. So I can define, let me define A to be a float, and it will let me do like 0.4, and it knows that 0.4 is a float. I could probably also define a prime as a real. But floats are notoriously difficult to prove anything about.
Yeah.
Like they don't, their addition is non-associative. And if you have non-associative addition, you're kind of like, you can't really do much with proofs. So I know there's a professor in America called Tyler Josephson who's working on chemistry and looking at using like how can you go from floats to reals when you're trying to prove stuff, you use reals, and then you kind of turn those to floats in the end when you're trying to do the simulation, when you're running the simulation. So you prove things with float reals and then you run them with floats. And there are ways to do this in a way that kind of works well with lean. And I would like to do this, like the definition of an eigenfunction of the harmonic oscillator is currently defined in terms of real numbers, so you can't evaluate it. But I would love if you were able to turn that real definition in terms of real numbers very quickly or very like automatedly into a definition in terms of floats that you could evaluate.
So when you're evaluating real numbers, then does it do symbolic manipulation or does it compute values? So if I have, I assume that you can define the square root function over the reals, right? If I give it two, what's going to happen? Does it give me square root of two as an evaluation, or it gives me?
I suspect it's not going to be. I think it's just not going to be evaluated. It's not going to be computable. Well, okay, that's a bad example. Oh, it is computable. It's going to give me. Oh no, it's not. Okay, yeah, it's not computable.
Oh,
So even addition, even division in the reals is non-computable. So if I go like 1 divided by 2 and assume we're in the reals, it won't let me do it. Because it
uh,
says division of the reals is not computable. I
okay,
think I think this is a general fact about real numbers that
okay,
division is not computable.
okay.
You can't compute division of real numbers.
Okay. Well, at some point you're going to have the problem that you're not going to be able. And as I said, either you do symbolically, but then
Yeah,
sometimes symbolically you're not really evaluating because sometimes you just get the expression that you've put in, so it's not really
yeah,
evaluating, or you can't do it because you're not going to have the infinite precision of the real. So it's okay.
yeah, yeah.
That's how they decide to.
One of the things that I've been doing, which hasn't worked great, is that most of the things that we actually deal with in physics, like the Pauli matrices, these sorts of things, they're defined in the reals, but
Yeah.
actually they contain like rational numbers and integers and things that you can actually compute. Um, so working out like proving stuff where you have like um, turning equations where you have, for example, the rational numbers and kind of like following injections back. So you get something in the rationals rather than in the reals, and then computing that is something that a trick that I've been playing. It's not great, but it's a way around this fact that you can get things that are
Interesting.
computable.
So does the set theory part, is the set theory part computable? So can I compute, sets from maps of sets and stuff like that?
Yes.
Yeah, I can. Okay.
Yeah. So if I wanted to, well, okay. So sets, so this is because it's based on type theory. Um, you can define like it will compute the type of uh it knows like if you have a finite type, so that's a type with like a finite number of elements. It's kind
Yeah.
of like what we would call like a finite set.
Yeah.
And another finite type, it will be able to find the finite type that is maps between those two, and it will compute those.
So
Um,
if I, let's say I specify a finite set with 100 elements, and then I specify what's it called, an equivalence relation, and then I say quotient, it would give me the sets of the quotients.
I believe so.
Okay. That would be useful for me in some cases. So
As long as your equivalence relation is decidable, which is
yeah,
not.
yeah, yeah. Of course, yes, well, yeah,
Yeah. If it's not decidable, then yeah,
yeah,
you
yeah.
won't be able to do anything.
Yeah, no, I mean the point would be right. So I'm trying to understand how much. So because ideally, right, what we want to have in 100 years would be things that you give the definition once, and you're able to do the computation, do the proof, and also write a human readable,
Yeah,
proof of what, and not with just a symbol, right? So I'm
yeah,
trying to understand what pieces are already there and
yeah,
whatnot.
yeah. The computable side of stuff is tricky.
The point is that if, of course, if I can't write a computer program to compute the thing that I've defined, I understand that Lean wouldn't be able to compute it, right?
Yeah,
But
yeah,
if I
exactly.
could write it
Yeah,
because I can go through the set and,
yeah,
check, then it would be nice if Lean could do it. But
yeah. I mean, so one of the, I mean, there is an example of this currently in Fislean, which is um what is it? It is related to this thing called Wix theorem. And so Wix theorem, you basically have a list and you want to pair up elements in that list.
right, yeah, exactly, yeah, yeah. Something like that.
And so you can, I'm trying to find the file. It's in quantum field theory, perturbation theory, with contractions. It's probably gonna be in this one. So what we can do is let's say, oh, didn't mean to press that button. So a lot of the stuff related to Wix theorem and Wick contractions is computable. So imagine we had four fields. Let's see, before I speak, yes, good. So imagine we have four fields,
Mhm.
and we want to find all the Wick contractions between those four fields. So Lean can compute that. Lean will tell you all of those Wick contractions. So you can, for example, find the cardinality
Mm.
of that set, and Lean will tell you it's an executable function, it's executable language. Everything in this file is computable. So it will tell you, okay, if you have four fields, there are 10 Wick contractions.
Okay, yeah.
Um, and it knows, like, if I wanted to prove something about these Wick contractions, I could get Lean to automatically go over the set of those Wick contractions
Mm.
and prove stuff about them for me.
Okay, cool.
Yeah.
All right, let's go back to the harmonic oscillator. We're taking lots of detours here, but yeah.
Sorry, yes. Yeah, okay. So harmonic oscillator. So the Hilbert space of the harmonic oscillator is to find a square integrable functions. And then
Mhm.
if you dive deeply into quantum mechanics and like what actually is the Hilbert space, you realize it's not actually square integrable functions. What we mean is almost everywhere equivalence classes of square integrable functions.
Yeah.
Um, so it's defined as proper as I can find the definition, which I believe this is the correct definition of the Hilbert space. So this file is basically look, this says, okay, the Hilbert space, we're going to define that as square integrable functions. Um, and then I proved a bunch of stuff about like making it easier to work with the Hilbert space. So
Can you pick one so that we
yeah.
can look at it and see?
Uh, let's see. Well, why don't we? This is probably tricky because it's like detailed measure theory, um, which is not that. Right, I'm not an expert in for sure. Um, so why don't we skip over to the harmonic
Okay,
oscillator,
let's go back to yes.
and then things are slightly more classic, like things are slightly more in terms of more basic objects, let's say. Um, yeah. So what is the harmonic oscillator? So what I've done is that I've defined the harmonic oscillator and as a type. And what this type has is it has three fields. So it has a mass, which is the mass of the harmonic oscillator, this constant called reduced Planck's constant, and the frequency of the harmonic oscillator. And then with some conditions that all of those quantities are positive. You actually don't need the mass and the the frequency to be positive. You just need them to be non-negative, which is going to require a refactoring of this file at some point to make that true. But this is a start to this.
So
So
those H bar, and H omega, those are the names of the constraints.
yes, they're the names of the constraints. So if I wanted to use this constraint,
Ah, okay.
I call it yeah, I just call it H bar.
Okay.
I could call this whatever I wanted. There's
Okay,
probably
but the constraint is not on the definition. So the
no,
fact that the mass is non-negative, it's a separate thing from the definition of the mass.
yes.
Okay.
So lean, I mean, there probably is a type where that is included,
Ah,
but it's easier to separate them for now.
okay.
But yeah, so lean knows what's a definition and what's a constraint. So with all of the definitions, it's got a doc string, and I haven't put a doc string. You don't have to put doc strings for constraints. Well, you don't have to put doc strings for anything if you don't want to, but it's good to put doc strings. So yeah, and then what this file is, so every file in Fistline, and the same for Mathlib, basically every key topic has a basic.lean file, and that's kind of like the basic definitions, kind of like the starting point of the file. So with the harmonic oscillator, you can define something like the characteristic length of that harmonic oscillator, and it's defined as the square root of Planck's constant divided by the mass times by omega. That's just like a standard definition in this folder. And you can start to prove theorems. So let's say we wanted to prove that the characteristic mass is positive. So we can work, well, why don't we work? Should we work through this proof?
Yes, just to, okay, so again, the first, like the eta pos, that's the name of the lemma.
Yeah, that's the name of the lemma. So if you want to use that lemma in the future,
Okay.
call it, yeah,
And
Kusai.
then the fact that 0 is less than that, that's the actual statement of the lemma.
Yes. So the thing that's between the colon and the colon equals is the thing we're trying to prove,
Yeah.
or the thing we're trying to provide like a type, an element of that type.
Okay. And then by introduces the proof, and now,
Yeah. So you
and
don't
now,
have like there are different types of proofs, but by is kind of like the standard tactic-based proof. So you'll see, so if we look at the right-hand side of the screen, we get what's called the
oh
tactic.
wait, previous question. What does the at simp mean?
Ah, yes, there is a simp database. So Lean has this tactic called simp, which doesn't work here, but it's basically if you're familiar with like Mathematica or any of these programming languages that simplify expressions. Simp is
Uh,
basically a tactic that will simplify expressions. And it does this in Lean by using rewrite rules. So what this simp means is that this tactic in the future can use this lemma.
oh, okay. I
So it
understand.
adds it to a database of lemmas that this tactic simp can use. So when it's trying to simplify things, it can use the fact that Cirrus let's say.
Yeah. Okay.
So that's all that means. Yeah, so we get on the right-hand side of the screen, we get this thing called the tactic state.
Mm.
So what this tells us is that we have something called Q, which is a harmonic oscillator. So with this Q, we have its mass, we have H bar, and we have everything in this file that we proved above. And we get the thing that we want to prove, which is this thing here. So then we can like start to apply tactics. So one of the tactics is rewrite. So we could rewrite Xi, and that will just replace Xi in this expression with its definition. So replace it with the
Okay.
square root of Q times Xi. That, and then we can start to apply lemmas. So we can apply that so that the square root is positive. So we can hover over this. So this lemma says that the square root is positive if and only if x is bigger than 0.
Mm.
Square root of x is positive if and only if x is bigger than 0. So we apply that, we get, so our lemma changes from this here, which is the
Yeah,
square
which
root,
is the square root and the square
it
root
gets
is
rid
like,
of the
yeah.
square root, basically. And let's say we didn't know what that lemma was. Let's say we didn't know what to apply here. We could do apply question mark, and Lean would go through all of the things, all of the lemmas that it has, and it will see, it will try and ask, what is a good thing to apply? What can we apply here?
Okay.
Um, and it gives us a bunch of suggestions. I mean, actually, these first two leave the goal in the same place, so
Yeah.
we could click that and it put it in there. We could also try going exact question mark, and it will see if it can close the goal for us. It will see if there's a lemma that's exactly the same as the thing
Mm.
that we're trying to prove. In this case, it's not, so that doesn't work. Yeah, so we can apply that, which takes us to this, and then this diff positive says that if A and B are positive, A divided by D is positive. Sorry, A divided by B is positive. So we split that, and then we get two goals, one of which is that H bar is positive, and one is that um, M times by omega is positive. And then this
Ah,
first goal,
we
so
already
yeah,
have
this
that.
dot kind of means restrict to this goal.
Mhm.
And then we have a proof of that because we know that Q has this property that HH bar,
Yeah.
which is positive. So that proves that lemma, and then we get no goal, um, which does that for us. And the second one, uh, we use this other lemma, which is that the multiplication of two positive numbers is positive. And we know that M is positive, and we know that omega is positive, so that we know that we can prove this goal that M
Mm.
times by omega is positive. And this is kind of a more constructive proof in the sense that I'm going through it step by step. I'm not using really any powerful tactics here. But like other proofs you use like the simp, which simplifies expressions. You use this tactic called ring, which basically simplifies problems in ring theory for you.
Mm.
And there are a
Yeah.
bunch of other really powerful tactics like that.
All right, let me get another couple of our comments from the chat. So basically, simp is the tactic that Link considers to be trivial. It's the see what you can do it on your own tactic. That's the fair characterization.
Say the last bit again, sorry.
It's the see if you can do it on your own tactic.
Kind of, yeah. There are other tactics like this. So there's one called ASOP, which is I forgot what it stands for, but it basically searches for simple proofs. But yeah, simp is off that start. Simp is like it's not necessarily asking can it prove the result, it's asking can it simplify.
Right.
Um, so let me see if I have an example. Well, okay,
So
here's an
basically, if you have an expression and you just want to,
make it simpler.
yeah.
Yeah. So I mean, here we have an expression here. I apply simp and it becomes this.
Right, yeah. Okay.
So yeah, ignore all of this is basically just me making it more efficient to run by telling.
And then you're telling what the type of simplification rule to use. Okay.
Yeah. So if I get rid of this, it should still work. Actually, it
Yeah, yeah,
does.
yeah. But it's gonna take some more time. Yeah, I
Yeah.
understand.
Yeah. So I can restrict its domain.
Okay, so is there a reason why you always use zero less than x rather than x greater than zero?
Yes, there is.
Okay,
0 less than x. Because greater than is defined in lean
to be the other way around.
to be the other side of less than.
Yeah.
So less than is defined like as a proper thing in lean, and then greater than is defined as kind of like the inverse of less
Okay.
than. So less than is kind of
More efficient because you are, yeah,
yeah.
skipping one step, so it's gonna find things more. Okay, so
Yeah.
this is standard in order theory. In order theory, you always define the less than instead of the greater than. So I guess that's.
And more generally, right, it's part of being consistent. If you define everything in the same way, it's easier for these like tactics, these search tactics to find that result. If everyone's doing different conventions on less than versus greater than, it's gonna be you're not gonna be able to find half of the tactics because
Yeah,
half of the lemmas because half of them use greater than, half of them use less than.
yeah,
There's
yeah.
some sort of like convention going on here as
Okay.
well.
Yeah, you have to double all the lemmas and stuff. So
Yeah,
yeah.
exactly. Yeah.
Okay, so do you know whether SIMP uses some equational automatic theorem prover? Because given the database, the proof itself can be very non-trivial to find and may include thousands of steps.
Can you repeat that?
Sorry. Do you
Sorry.
know whether SIMP uses some equational automatic theorem prover? Because given the database, the proof itself can be still very non-trivial to find and may include thousands of steps.
Yeah, I don't know.
Okay.
As far as I'm aware, what SIMP does is it has a list of results, and those results are somehow like ordered in priority,
Yeah.
and it basically searches your expression and says, "Can I rewrite this rule with any of these results?" And if it can, it does. And as far as I like, as a order one approximation of my understanding of what this thing is, this is all it's doing. It probably is doing a lot more clever stuff behind the scenes.
Yeah, it's my understanding. It's the same thing that things like Mathematica or all these things that do Maple 5. They basically have some heuristic and they massage thing in a pre-ordered way. There
Yeah.
isn't like a real intelligence that it's trying to fiddle
Uh,
with it. Again, inference engine were a little bit more sophisticated, in which you're given an end goal to an inference engine, and then it's trying to find a path with all the inferences to find the goal.
yeah.
But yeah, I don't know what you know the Wolfram people are doing because they also have some type of symbol manipulation stuff. But
Yeah.
there they are interested more in the computation than this. This is more theorem proven. They're interested
Yeah.
in actually
Yeah.
computing things and seeing all the possible expansion of all the different expressions. So.
Which is an interesting point. I mean, one of the like Wolfram and Mathematica. I mean, Mathematica is this thing called a computer algebra system, which
Mhm.
isn't a computer algebra system, it's a theorem prover. But physicists, and we're used to using computer algebra systems, we're not used to using theorem provers. Um, well, at least I'm used to using a theorem prover, but most physicists aren't. Like one of the things that's happening in the lean community is there is a push to try and make lean have have the power of a computer algebra system to
Mhm.
allow you to do some of the more like computational stuff, like
Mhm.
find the rank of a matrix or multiply vectors or things like this.
Yeah. I'm much rather that all these things had some kind of come si chiama? Like uh, like boundaries where you can ship back and forth the structures, so that there's a tool that does the algebra, but from Lean you can set up the problem and prove
Yeah.
that the problem is correct, and then the other guy. I'd rather. Like this is something that unfortunately in computer science it never happens. Everybody's like doing their own system, and then it's very difficult to
To
make the
move
things
between them.
interact. Yeah, yeah, yeah.
Yeah.
Which is
And,
like the plague for different software languages, because then you're stuck with your own libraries and you can't use the libraries of another language because everything is like there are mismatch in yeah. So
yeah, I mean, I mean, okay, within one single language, this is one reason why a repository like Vislean is better than having like 10 different repositories for physics.
that I agree. Yes, yeah,
Like you don't want 10 different repositories for physics. The rate that Lean updates is like once a month you get a new update of Lean. And if you have 10 different repositories, half of which don't update on the same time schedule,
yeah,
it becomes impossible to manage. So
agreed.
this is
Yeah,
one main reasons why I'm a very big advocate of, like, let's just have one repository. Let's make sure everyone's working on the same thing. Let's help each other improve. People improve what I've done, I improve what people's done. We make this good together rather than And like one person can be in charge of upgrading it at the right time, for
Yeah.
example.
Now,
Uh,
for standard libraries, that's sort of how you do it. There's
yeah,
no other way. Especially when you're trying to then implement new features that it's critical that the other parts of the library, get aligned. So,
yeah,
you
yeah,
change the collection classes in a language, you want to see all the other libraries now to use the new collections. And if everything is, I mean, Python 3, part of the problem of the update was also having everything sort of, yeah, it becomes like that otherwise.
yeah.
Yeah. Oh, yes, we, the Wolfram people, also have some rewriting rule database for simplification and also some great ATP behind find equation proof that searches the proof given a list of axioms. There you go. So,
Nice. What I would love to see in Lean is a way to interact with a like you want to find the rank of a matrix, right? Ship that off to like Mathematica
mm,
or a similar like computer algebra system and get like Mathematica to give you back a certificate of the proof. So something that Lean can
yeah,
check very quickly that is true without having to do the like hard computational, which people at like Mathematica and Wolfram have
right,
have
right. There, yeah, that's exactly.
they're the experts
Nick,
in
do you
that. So
know if there is a way to make Lean interface with Wolfram stuff, or it's just completely different?
there used to be a way to do it with Sage. Um,
I see.
I think one of the I don't know if there is a way. So there's this tactic called Linarfa. I'm gonna pronounce that wrong. So which basically does this for problems problems like show like you've got a bunch of inequalities and a bunch of equalities in like the reals and you want to try and show that something is true. What Linarfa does is it ships it off to Sage, gets a certificate back. Oh, sorry, not Linarfa, Polyriff is the tactic I'm thinking of. It ships it off to Sage, gets back like a certificate, and then brings it back.
Okay.
Uh, this is like a, yeah, this is one example where it has been used, but it's definitely not like a big thing.
Oh,
Uh,
cool. So that gives me hope. Also, Nick says that he has seen some tactics that interface with Mathematica in both directions. So, good.
yeah, there's tactics that interface with artificial intelligence. Like Lean Copilot. So you can, I don't have it installed, but
Okay.
you'd be able to write something like search proofs, and it will use an artificial intelligence model, and it will give you, if it finds a proof, it will give you an answer. And yeah, so that's like one of the things that I think is like the next 5, 10 years is going to be, artificial intelligence is going to be able to help us write proofs in the system.
But in that case, it's still like matching of things that he had already seen. It's going to be difficult for an artificial intelligence to create a new proof, I assume.
Um, yeah, I can't comment on this because I just
Yeah.
don't know.
Because
But
every time that I try to make, right now, the sort of LLM type stuff for doing math, they're just, they're absolute nonsense. So, but maybe if it's trained on things like this, there is more of a chance. But yeah, so
yeah, the advantage of things like this is that they can get feedback from the
yeah,
system.
yeah.
You don't have to have a human giving them feedback.
Yeah.
The artificial intelligence can give them that. Sorry, the Lean can give them feedback of whether their proof is right or wrong. Um, yeah, I know a lot of people. I mean, Google DeepMind proved took part in the Math Olympiad using Lean.
Mhm.
Uh, But Math Olympiad problems are different from like research level maths problems, which are different from research level physics problems. Uh,
Yeah, okay.
so
Yeah, okay. You would have to train specifically on the different topic.
yeah, or somehow like
Uh,
you give it the context
yeah,
of
yeah, exactly.
you
Yeah.
give it the context of everything that's come before it.
Mhm. Interesting. Are there any other questions from the chat? even more in general, or should we continue this? What do people on the chat
Yeah,
think? I've been
what
basically been driving up to now with my own curiosity, so maybe I can see what people want to. Otherwise, we just continue what we have been doing. We can go back to the example of the harmonic oscillator if there are no specific. Okay, let's go back to the harmonic
okay.
oscillator. I don't see anything propping up on the chat. Okay, so we saw that you were able to prove something, and so all these lemmas are basically similar things, I assume. And
Yeah.
the tactic is always to break the whole thing in very small pieces.
That tends to be the one. There's no harm in breaking this thing up into small lemmas.
Okay,
So why not? Because then you can use those lemmas again.
yeah,
Uh, there's no point of having like a ma I do okay. There are really long proofs in this sort of thing, which I haven't broken up. But it is better to split it up into small lemmas. It's just easier to manage, and
okay.
it's just easier to understand what's going on, and it's easier to use those things again, so you don't have to prove them all the time.
So
Um,
can you show us something that it's a little bit more complicated, that it's longer, just to give an idea of what? So the thing that worries me is how much doing something that by hand you can say, yeah, yeah, this is obvious, whatever, and then you can't just tell this is obvious to Lean.
No.
And
Um,
I know from computer science, computer engineering, like software engineering, sometimes doing simple things it just takes like hundreds of lines of code, and
yeah. I mean, the problem is like what might take me 100 lines of code might take somebody else like a line of code if they
yeah,
know the right thing, if they know the right technique. Um,
so here what we're trying to prove.
yeah, here's an example. So this is basically so okay, I've skipped a couple of files ahead and
Yeah,
I've
yeah.
defined the eigenfunctions of the harmonic oscillator.
Okay,
Um,
so remove the tooltip. I wanted to see. Okay, so lemma.
sorry.
There you go. Eigenfunction moves. So now the lemma has a parameter.
Yes. So either so Lean allows you to do one of two things. It allows you to put the parameters here,
Uh-huh.
or I can put them here as for all statements. It's just I'll have to,
Okay.
but by putting them here, it's just like a shorthand for saying for all n and m, which are natural numbers.
Okay.
This is true. Um,
And so you're proving that
so this
I.
is yeah,
Go ahead. Go ahead.
it's a really simple, it's just a really stupid proof. It's just saying I'm going to multiply two tensors, I'm going to multiply two eigenfunctions together, and I'm just going to rewrite that equation in a different form because I want to use it later. Uh,
Okay. So yeah, I have to get used to the syntax. So you're saying that so those are two eigenfunctions. The n and the p are the eigenvalues.
Yes.
But
Yeah, they're like they're the integer associated. So for each integer, you get an eigenvalue of the harmonic oscillator, zero being the ground state, and the other.
okay. So those are the not just any eigenfunction. They are the eigenfunction of the harmonic oscillator.
Yes.
Okay, so they are parameterized by a natural number, and it starts from zero because also you are more a computer person. I've been having this this very heated discussion with some mathematician that tells me that no, natural number starts with one, and
Yeah, no.
yes,
I
this is
my math is dictated now by what's in MATLAB, and MATLAB has natural numbers starting at zero, so I have natural numbers starting at zero.
anyway. So okay, so these are basically the Hermite polynomial. That's why there is Phys Hermite later, right?
Yep, exactly.
Okay, okay.
Lean has been clever because I've been naughty and I haven't introduced this X.
Hmm.
Lean has implicitly put that in for me. So if I hover over this, it will say, look, you've actually introduced an X. Um, so it's clever, it can do that. Um, yeah, and then I'm just kind of like rewriting this as the product of two Hermite polynomials times by an exponential times by a, so naively, what this proof should be is that you expand these eigenfunctions,
Mhm.
and then it's just properties of real numbers to solve this.
Okay.
It's just arranging equations using the fact that the square root of x squared this X.
Right.
But there's a bunch of technicalities that come into this. Um,
Yeah.
like the
And the
square root of,
domains.
yeah, I mean, like the square root of X squared is only X if X was positive to start off with.
Yeah.
So there's a bunch of stuff like that. You just have to grind through. And ideally, all of this should be, you click a button and it's done,
Mm,
but you have to grind through.
okay.
So yeah, I can walk you through the proof if that's something you'd want, or
Unless there is somebody else that wants to ask other things, but if there is nothing to do, yeah, I'm curious to see how cumbersome the whole thing is.
yeah. I would say it really, really depends. Like there have been times when most of the time things are fine, and
Mhm.
then other times you just get stuck in something like what's called like casting problems, where you want something like a natural number, but what you've got is an integer that's actually a natural number. It's much like more complicated scenarios than that, but like that sort of problem and like
Yeah,
basic results sometimes you get stuck with. But there's a general rule which I learned probably far too late, that if you're running into problems, like if you somehow end up having to deal with like stupid things with like zeros and ones and like whether something is type correct or not, you've probably made the wrong definition of what you're doing.
yeah, yeah,
Probably a better definition you should have started off with.
yeah,
Um,
yeah.
so
So,
like
these are normal problem when you're doing software development.
yeah,
So it's very common that you have two libraries and you need to use, but the objects are different. And so you have to do the marshalling and unmarshalling from one side to the other. And so you basically are stuck. 80% of your code is just doing the translation. So it's
yeah.
not something that is lean specific.
No, okay.
Also, even when you're doing math proofs, sometimes you're stuck saying, "Oh, wait, I need an index for that, and then another index for that." But then,
Yeah.
so those are even there are the math problems when you're doing the proof. So here you basically have a little bit of a combination of the
Yeah,
two things.
exactly. You have the worst of both worlds in a sense.
So yeah, so and that might be that you have combination of those, so you might have a combinatorial problem between the translation. But yeah, so I agree. Like if you have that's where I was surprised that and again, I might see the reason. So if I were software mindset, right, and I
Mhm.
have the mass, and the mass has to be a zero or greater, to me that's another type. I wouldn't have the other type of a constraint because then you just might get it wrong because at some point you don't realize it. So it's better to have another type that is. But then I understand that you are going to have all the proofs and all the other lemmas that you can use on the real numbers and not on these other type. And then you sort of might be shooting yourself in the foot because then you can't use the automatic proof things. And yeah, so
It's also, I mean, like also the fact that it helps you keep track of when you've needed to use an assumption. Like maybe I didn't need to use the fact that n was positive to do any of this. I
yeah,
can, I,
but so on physics ground, the negative math it just doesn't make sense. Like it's just it just doesn't work. It's like saying, "Oh, I have an imaginary mass." What does it imagine? It's not a physical thing, right? So yeah, that I'm perfectly fine. Even h bar is a constant. It's not even a real
yeah,
number.
we know the number that H bar is.
Right. It's in fact we even defined it to be something, right? So
Yeah.
it's really a number. It can't be anything else.
Oh yeah.
And so like pretending that those things are not like it's basically generalizing a problem that can't really be generalized. But
Yeah.
again, I don't know what happens in lean if you have too many types that are different from each other to sort of have the types that you really need in that specific system, and then you're going to have the same problem with the less than and greater than, right? That
Yeah. 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 Yeah, in general, you don't wanna, and people have told me, like I've been guilty of this.
Mhm.
Uh, like okay, Hilbert. Okay, I've been guilty of this with the physics hit Hermit polynomials. The physics Hermit polynomials, if I go to their file, they are defined as a polynomial over the integers.
Okay.
But we consider them as physicists as a function from the real numbers to the real numbers.
Okay.
So I can make it, so I could either take, I could have this definition of the Hermit polynomials as polynomials, and then I could also try and define them as functions from the reals to the reals. But that's bad because you don't want to have like two conflicting definitions. What you want to do is what's called casting.
Yes.
So
Yes.
Lean automatically knows you can actually this is a polynomial, but you can treat it as a function between the reals and the reals.
Yeah.
And when it is in that context, it should be thought of as in that way. And when I first wrote this harmonic oscillator, I had both definitions, and then I posted this onto the Lean Sulip chat, and they were like, "You should probably only have one." Um,
Yeah.
so I had to refactor.
Okay. Yeah. So related question on the chat. Did you include physical units in some way? Could you do
No,
dimensional analysis?
no. So yeah, so there is this group of Tyler Josephson, that is interested in units and dimensional analysis, and I think they are, yeah, I think they're working in this direction.
Okay. So I did some work again 20 years ago when I was the interesting bit of that I came out for the dimensional analysis is that you can't really do it automatically
Hmm.
in the sense that so suppose that you have a cylinder, right? And
Yeah.
the volume of a cylinder is the height times the radius times the angle. So in principle, you have radians, let's say meter and meter.
Hmm.
And now you could do two things. You could take the angle and multiply by the radius, or so that's the surface, not the volume. I'm thinking the surface, right? So there would be radius times angle gives you the length on the side, and then you do the vertical height, and then you know the part that you're taking, the section that you're taking, the vertical section of the area.
Yeah.
So the point is that if you take the angle and multiply it by the radius, now you have a length. But if you take the radius, the angle and multiply by the vertical height, you don't have a length. You have a length time an angle because the angle and the length are going to be, so the length is going to take away the angle only when you're doing the right length with the right angle. And it's because the angle is really a ratio between the length on the circumference and the length of the radius, and so you have to take out the right thing. So that makes it something that you can't really technically completely do it automatically unless you know how the pieces are built into the equation itself.
Yeah.
And otherwise, you need to provide hints. So it's not that simple. And then there are even worse things like some units are how can I say? They are units of differences, and some are units of absolute. And the way that you change the absolute unit and the distance and the difference is different. So, for example, if you have a temperature in Celsius and you want it to convert to Kelvin, you don't know how to do it unless you know whether you have an absolute temperature in Celsius or a difference of temperature, because the difference of temperature between Celsius and Kelvin remains the same, while the absolute one changes. So it's not enough to say, oh, I have a quantity in Celsius converting into Kelvin. You need to know what you're doing.
Mhm.
So it's because again, this was maybe 25 years ago. I said, "Oh, I want to create a computer language that takes all these things automatically," and
Yeah.
then I said, "No, you can't. You can't. The only thing that you can do is provide places where people can put the hints about the unit and the dimension and so on. But at the end of the day, the guy who is creating the function so that gives you these inputs and outputs, he has to put in his mind and try to understand what's going on. So So
Yeah.
yeah. So I
Yeah.
don't know how much lean can do that. There are like significant problems. And then when you do tensor stuff, then it becomes then it
Yeah.
becomes a lot of fun. But
Yeah.
you can actually automate some things there. But anyway, there is another comment from Nick, who is the person who is one of the Wolfram people. He actually works on Wolfram Strap, which is great that he joined actually. And
Thanks.
Lean has tooling problem. Writing proofs like this is not meant for humans. LLM should do it more often. Humans need better apps to simplify and gamify processes and outsource code writing to AI. That's a
Mhm.
mistake.
Yeah, absolutely agree. I mean,
Yeah. So-
I would say it's fun. Like lean is fun. But the like one of the problems I've had getting people involved
yeah,
is
yeah.
the learning curve to learn lean. For me, it was worth it because like I kind of have made my recent career on this sort of stuff. But to the average physicist, for sure, the learning curve to learn lean is currently not in their best interest to do that. And it's difficult. And you have to pass quite a high boundary if you want it to be fun and you want to be like you get to use it. So any ways to make it easier with AI, to gamify it, to do all of the stuff, very, very much for.
Yeah, but you still need the core. So the AI at some point has to
Has to
write
have,
stuff, and somebody has to go manually to make sure that these things are they make sense. So
yeah, I mean
again,
this.
it's probably what I was saying before. I'd like that there would be an ecosystem of different things where they can talk to some kind of common
Central.
currency for this stuff, whatever it is, if it's lean or something else. But
Yeah, like um, I forgot what I was going to say. I was going to say
sorry.
what it was. No, it's gone.
Oh, sorry.
It's okay.
You can review the part of the live and see if you
Yeah, see if it
remember.
comes back up.
There is an comment from Nick. For Nick, by the way, are you familiar with functional differential geometry by Gerald J. Sussman? I think it's a good source for formalizing this stuff. I
Yeah,
don't know
no,
what
I'm
it is.
not.
Okay. We are ignorant,
Yeah.
and our ignorance now is forever recorded online.
There's many things I don't know. Like, I
No, no, I
prefer,
know, but I don't want to tell right now.
yeah. Yeah, like, yeah, I think, I know what I was going to say. I remember the thing that I was thinking about. Um, I think like one of the parts of this thing, yeah, you're right. Hopefully AI is going to be at a point where it can help. Like I'll be able to right here solve this proof, and it will solve it. But for it to do that, it needs examples and it needs context and it needs, you know, things to learn on. Starting with this project, like now, before these things develop, I think is beneficial because then you have the context
Yeah,
which you can use to do further things. So we're kind of providing the bedrock here,
yeah, yeah,
uh, from which it can hopefully be built upon. And like, if we're not afraid to, when new technologies come out, to adopt them, to go, okay, this is good. Let's change the way that we're working and let's adapt it to this. It might involve like a refactoring of the library. Who cares? Like,
yeah.
it's going to be work now, but if this is going to try and make this like make this a longevity thing, you need to change. You need to adapt to these things.
So it's been an hour and a half. So we we should thinking of closing.
Yeah.
Are there any other questions or comments from anybody? I always have to wait because there is delay between when I talk and I see the messages and
Yeah, I'm sorry we didn't. Went on a lot of tangents, which is probably my fault for taking us down those
no, no,
tangents.
but it's fun. I mean, it's meant to become like this. Otherwise, it's no
Yeah,
fun.
probably
So
better than me just speaking.
yeah.
Not.
No, it has to be a little bit like that. Yeah, so if there are no other questions and so on, we can probably stop it. And then thank everybody for interacting. Thanks to Cram, Tobias, Nick, WWKK for being active in the chat, and thank Joseph for everything.
Thank you.
And
Thank you for having me and
and maybe we can do this some other time as well if there
yeah.
are some updates on things that are interesting and so on. I think as I was saying before when we chatted, like we both do think that we need some type of more interaction between math sides and physics sides to sort of develop pieces that are more apt to. So in terms of units, so one of the things that I also think that we're missing in math is a formalization of a unit system that actually makes sense. And I had some ideas, but also that it's a whole research topic, and also for differential geometry, there should be a way to define those things so that they are. So anyway, there's a lot of stuff that needs to be, and my particular interest is not to formalizing the thing in the math that we have right now, is to really find the mathematical structures that are more fit more for physics. But it's still we need to make math and physics work better across each other. So among each other. I don't know. I don't know what the term is in English, but anyway, so that the transition is more smoothly. So I think this is a topic that is interesting to both of us. So thank you again for everybody that showed up, and we'll see you next week. Bye, Joseph.
Thank you. Bye.